Now that we've discussed how two different substances mix to form a solution, which follows this rule that like dissolves like, I want to focus for a minute on electrolytes. So an electrolyte is defined as a substance that'll conduct an electrical current through water. Something that does not do this would be a non-electrolyte. And that doesn't really, I think, convey what's happening very effectively. But if we look at this on the molecular level, what conducting electricity through water means is that your electrolyte needs to be an ion. So you'll have anions like chloride and cations like sodium in solution. And these charged particles allow electricity to be conducted through water. A non-electrolyte will have a neutral charge. So hydrogen peroxide is an example of that. Water itself can conduct electricity, pure water. That's because water will react with itself in an acid-base reaction to form hydroxide ions and hydronium ions, which we'll cover when we talk about acids and bases. So it's this electrical current that is depending on ions that dictates if it's an electrolyte. So if you hear electrolyte, know that we're talking about something that will break up into charged particles when it's dissolved in water. Now the interactions that are happening here are ion-dipole interactions. So like does dissolve like, but our ions are not going to be polar. They're just going to be charged. But being a charged particle is kind of like an extreme version of being polar. When something's polar like water, there is an uneven distribution of electrons. So that way there ends up being a partially negative end to the molecule and a partially positive end of the molecule when it has a dipole moment. And so a negative or positive charge can interact with something that has a dipole moment. So the negative end of a molecule can interact with a positive cation, like sodium. And this interaction is pretty strong because we have a full charge from our ion interacting with a partial negative charge. And it's that same opposites attract Coulombic force that is bringing these together, and opposite charges being electrostatically attracted to one another. On the other end of water, where it's partially positive, it'll interact with an anion that's negative. So we get that positive-negative interaction again for another strong ion-dipole interaction. And so when an electrolyte is added to water like sodium chloride, we can recognize that it'll be an electrolyte because it's an ionic compound. And not all ionic compounds dissolve in water. We have solubility rules that help us predict that we learned about when we talked about precipitation reactions. So if we can use our solubility rules to predict that it will dissolve in water, then our ionic compound will split up into its ions when it's in water. So aqueous sodium chloride will really be sodium ions floating around in water and chlorine ions floating around in water. And they aren't really bonded to one another anymore. Instead, they're interacting with the water. Oops, sorry. Just flipped through all the slides. And as we said before, what this looks like is if I have a positive ion, it'll be interacting with water molecules that will surround it completely. And so there isn't space for it to interact with the chloride anymore if it's completely surrounded by water molecules. And so the partially negative end of all these water molecules will surround this ion, and that makes it soluble in water. And the opposite would be all of the hydrogen ends interacting with a negative charge from our water molecule. And so here is this idea about conducting electricity and how this comes in. Something that is a strong electrolyte will, we call it dissociate completely. That means it'll dissolve completely as its ions. So our sodium chloride will break apart into all sodium cations and all chlorine anions. And if we put a positive and negative electrode in this, the positive cations will be attracted to the negative side and the anions will be attracted to the positive side. And this will create a current that lights our light bulb up. So if something is a strong electrolyte, it's another way of saying that it completely breaks the ionic bonds between them, or the acid-base bond, or the covalent bonds in an acid or a base. A weak electrolyte is something that this only partially happens to. So this example here is hydrofluoric acid, which is a weak acid. And so some of these hydrogen fluorine bonds break, leaving us with H plus and F minus as ions in solution, but not all of them. And so because only a % of these bonds break, we will see less electricity conducted because we'll have less particles in solution being attracted to the positive and negative anodes and cathodes. And so we'll have less electricity flow into our light bulb and shine. And if something is a non-electrolyte, this example is methanol. It won't conduct electricity at all because we don't have any ions to be attracted to the anode and cathode that are placed in the solution. So a strong electrolyte, all of our reactant becomes an ionic product. A weak electrolyte, only a percentage does. A non-electrolytes, none does. So give this example a try. You can pause the video and I will restart here in a second and solve it. But try to predict what are the products if these are both strong electrolytes. So if these are both strong electrolytes, they're going to break up into their ionic compounds completely. And so if this feels a little unfamiliar or rusty, I strongly recommend going back and reviewing ionic bonding. We'll basically be doing the reverse crisscross rule to solve these problems. So if I have a molecule calcium chloride, I'm going to separate these into the cation and the anion. And I'm doing that because one is a metal and one is a non-metal. And my non-metal is going to be my anion and my metal will be a cation based on their electronegativities and their ionization energies. So I can use the periodic table to determine the overall charge of my calcium and my chlorine ions based on the number of valence electrons they have. I can also do the reverse crisscross rule where I take the subscript and I know that'll be the charge on the other atom. And so that would give me calcium plus 2, which will be aqueous because it will be dissolved in water. And I'll have chlorine minus 1, aqueous in water. And I'll have 2 of those chlorine atoms, and that's coming from that 2 subscript here. Even though that 2 becomes this charge here, I still have a ratio of 1 calcium to 2 chlorine atoms. So it's important that I include that 2 so I have a balanced equation. Another way to think about this is to just identify your cation and anion and write those out. And from the mole ratio, I have 2 of them. And then use the periodic table to determine that calcium is always plus 2 because it's in group 2. And chlorine is always minus 1 because it has 8 minus, sorry, it's in group 7. And 8 minus 7 equals 1. And so we would have a negative 1 charge. The negative is going to again be because it's an anion in a nonmetal, and the positive charge is coming from the metal being a cation. All right, let's look at our next one. I see a metal, potassium, so right away I can pick that out as my likely cation. And then I see multiple nonmetals, phosphorus and oxygen. So hopefully after we worked on ionic bonding, when you see this, you recognize it as a polyatomic ion. So this would be all together. It's held together by covalent bonds, but it will have an overall charge. And you'll have the polyatomic ion chart to guide you with the charges, but you can also figure it out from the number of potassium ions you have. That could be the charge on your anion, and the number of phosphate ions you have becomes the charge on your potassium. Now, I think it's important to note that that PO4 is all one anion. So when I have PO4 written, I really have a subscript of 1 that isn't written there. So my potassium will have a +1 charge. It's also in group 1, so all of my group 1 cations have a +1 charge, and they'll be dissolved in water. I have a subscript of 3, so that means I will have 3 of these once they've been separated. It's important to not put that subscript after the potassium in the product side, because each of these have been separated now that it's not in the solid state. And then I'll have my polyatomic ion phosphate, and it'll have an overall charge of -3. And that -3 applies to this whole phosphate. And it'll also be aqueous.